Welcome back. All right, let's talk about something that is, quite literally, the secret sauce behind so much of the digital world we live in: database normalization. It's all about taking a messy, chaotic pile of data and turning it into something clean, organized, and, most importantly, trustworthy. Let's jump in. Okay, so take a look at this. On the surface, this table seems totally fine, right? Student info, their department, who the head is, their subjects, it's all there. But, and this is a big but, this simple design is basically a house of cards. It looks stable, but it's just waiting for one little change to make the whole thing fall apart. Let's see why. So let me ask you this. What happens if just one of those details changes? Say a department head moves on. With a table built like this, that one single update can set off a ticking time bomb for your data's integrity. And that brings us to the real heart of the problem. I like to think of these issues as the three villains of bad data. They're technically called anomalies, and they are masters at quietly corrupting your database without you even knowing it. First up, we've got the update anomaly. In our student table, you see Dr. Rao is listed as the CS department head for both Anita and Ravi. While if a new head takes over, you have to go on a hunt and change every single one of those entries. If you miss just one, boom, your data is now inconsistent. It's lying to you, telling two different stories at the same time. Next is the insertion anomaly. This one's a little sneaky. What if the university wants to launch a new data science department? With this table, you can't. You literally cannot add it to the database. Why? Because the table is designed so you can't add a department until a student is enrolled in it. The design itself is blocking you from storing perfectly good information. And our final villain, which might be the most destructive, is the deletion anomaly. Let's say Mina is the very last student registered in the ECE department. If she graduates and we delete her record, we don't just lose her info, we lose the only record that the ECE department even exists and that Dr. Patil is its head. The entire department just vanishes, wiped from the database. So, how in the world do we defeat these data villains? We fight back with a super powerful systematic process called normalization. This is our hero, a structured approach that brings order and sanity back where there was chaos. So, what is normalization really? At its heart, it's just the process of breaking down big, problematic tables into smaller, more focused ones. The goal is super simple. Each table should be about one specific thing and one thing only. This is how we get rid of all that repetition and protect our data. And this isn't just about being tidy. The goals here are very real and very practical. When you get rid of redundancy and store data logically, the database becomes way easier to maintain and scale up. But the big win? You get greater accuracy and consistency, data you can actually trust. So, how do we actually do this? Well, normalization follows a series of steps, or rules, called normal forms. You can think of them as levels of organization. We're going to focus on the first three, because honestly, they solve the vast majority of problems you'll ever see. Yep, our journey to a clean database has three main checkpoints: first, second, and third normal form. Each level builds on the one before it, and each one is designed to stamp out a very specific kind of data problem. The first rule, 1NF, is the absolute bedrock. It's super simple. Every single cell in your table can only hold one single piece of info. That's it. It's the one value per box rule. No lists, no comma-separated stuff, just one thing. Here is a perfect example of a table that breaks that rule. See this subjects column for Anita? It has two subjects just crammed into one cell. That's a huge problem. How would you even find all the students taking OS reliably? You can't. This table is not in first normal form. And the fix is to just split the record. We give Anita one row for each subject she's taking. Now every single cell holds just one piece of information. Just like that, our table is in first normal form. Easy, right? All right, on to second normal form, or 2NF. This is all about getting rid of what we call partial dependencies. It sounds technical, but the idea is that every piece of info in a row should be about the entire unique identifier for that row, not just a part of it. If a subject's credit value only depends on the subject and not the student taking it, 2NF says that credit info doesn't belong in the student table. It belongs in its own separate subjects table. And finally, third normal form takes on transitive dependencies. Let's go all the way back to our first table. The department head, Dr. Rao, doesn't depend directly on the student, Anita. He depends on her department, which is CS. See that chain reaction? Student points to department, which then points to department head. 3NF says we gotta break that chain. You create a separate departments table, and now everything is nice and clean.
Okay, that's enough theory. It makes a lot more sense when you see it happen. Let's take a brand new, messy table and walk it through the whole process, from chaos to clarity. So here's where we start. It's a single table that's supposed to track which employees work on which projects. You can probably see the redundancy from a mile away. The project location, Delhi, and the manager, Smith, are repeated for every single employee on Project P1. This is a classic recipe for disaster.
And here's the beautiful result after applying our rules. We've split it into 3 highly focused tables. All the employee info is in one place. All the project info is in another. And a simple little works on table just connects them. Now, if a project's location changes, you update it in exactly one spot. All those nasty anomalies, gone.
But, and this is really important to remember, normalization isn't some magic bullet that's perfect for every single situation. It's a powerful tool, for sure, but it's a design choice that comes with very real trade-offs. So here's the trade-off in a nutshell. It's integrity versus complexity. On the one hand, the advantages are massive. You slash redundancy, you prevent those awful anomalies, and you get consistent data. But on the other hand, splitting data into all these tables means you have to piece it back together for reports. That process, which we call joining, can sometimes make your queries more complex and maybe even a little bit slower. So let's just quickly recap the fundamentals. First normal form, one value per cell. Simple. Second normal form, make sure your data describes the whole key, not just a part of it. Third normal form, get rid of those indirect roundabout dependencies. But the goal, the whole reason we do this is always the same. Eliminate repetition and protect the integrity of your data. And all of this leaves us with one final big thought to chew on. We've just gone over the gold standard for structuring data. But in our modern world of big data, with these absolutely enormous data sets, where speed can be everything, is this kind of perfect organization always the most important goal? Or are there times when a little bit of planned messiness is actually better? Something to think about. Thanks for watching.